You know the Goldstone theorem, it says that every time you break a symmetry or a generator is not symmetric, you'll get a massless Goldstone boson. In the case of gauge bosons, it's even easier, right? We are obviously going to get a massive gauge boson because, well, let's do an example. Our SO3, I emphasize SO3 just to say that I'm taking a vector. Phi, transforming is O phi. O transpose O is 1. Determinant O is 1. So I write O as e to the I, say L, or T, sometimes called it, doesn't matter. Very often for SO we use L. And these are obviously imaginary, n-Hermitian, and therefore antisymmetric. That's another way of seeing that Lij, that Lijk is minus I epsilon I jk. The same old potential as before, it's just that theta is not a function of x. So I'm taking a local SO3 symmetry. And as before, I take phi 0 to be 0, 0, v. Or if you wish, I can write e to the I, Li gi over v, 0, 0, v plus h. Our usual trick. And I can sum over all three generator here because L3 automatic analyze the vacuum, right? From here, L3 phi 0, 0. This is not broken. Of course, you can never break the whole SO symmetry with one field. You can always rotate whatever vector you have in one direction, and what will remain is the rotation around that axis. Whereas L12 phi 0 is non-zero. So what I expect, that MA3 should be 0. There is no breaking in this direction. And I would expect here that MA1 is non-zero. And MA2. What else would you expect? Do you expect these masses to be different, same, A1 and A2? Equal, someone said? Why?
Because it shows the vacuum state in that form.
The SO symmetry, right. In other words, SO3 breaks down to SO2 through phi 0. And of course, gauge bosons are a geometry representation, so the gauge boson transform the same way as phi under the global. But there is always a local piece, I don't have to remind you of that. But globally they transform as this vector. In other words, A fields also, these three, A1, A2, A3, if I write like this mu, they also transform as O, A1, A2, A3. So if I look at around the rotation around the z-axis, right? If I write, what is L3? L3 is like this. Which is, no, maybe not. It's okay? No. No. Maybe it's better like this. No? Sorry? Maybe plus 1 there. Plus I. In other words, this is sigma 2 here, 1. Right? L3. In other words, A1 and A2, how do they transform when I'm in the subspace? As e to the I theta L3 becomes This is sigma 3. This becomes sigma 2. Correct? A3 stays invariant, obviously. This is a unity in this case. I'm just looking at the rotation around the three axes. The symmetry that remains. This SO2 is generated by L3, of course. L3 is not broken. So I'm curious what happens under my unbroken symmetry. You know, when I break a complicated symmetry, there may be SO145, whatever, under the whatever group I have. I'm going to organize my thoughts according to the unbroken group. I'm going to look at the symmetry there. For example, if the symmetry is SU3, then I know, for example, if I have octet, all of them should have the same mass. I don't have to calculate all the masses. So it's very useful to look always first at the unbroken symmetry and see how it would work, because that will relate particle masses. So I'm trying to see what happens under the subgroup that remains unbroken. And what is this? This, you know what it is. This is cosine theta 3 plus I sigma 2 sine theta 3. You agree? Because sigma 2 square is 1. It expands immediately, which is cosine, let me write C3, cosine, sine, minus sine, cosine, A1, A2. There was a mu index that I could keep if I wish. You know, when we look at the global properties of the gauge boson, we can often forget about the fact that it's a Lorentz vector. The way we forget about the electron. We don't think about the electron as a spinor where we look and the mu and how they transform under the internal group. You forget the spinor indices. So it may be convenient in the future. Here I'm keeping it just to remind you. So you see, this is the usual rotation of a fundamental field. So I expect them to have the same mass, okay? It's good to think before. Well, I can think after also. And it's going to be easy to see. Where do they get the mass? They get the mass from d mu minus Ig Li A mu y. I can write the internal index where I wish. And therefore, when it acts on phi 0, I want to read off the masses. It will give me what? L3 will give me 0, so A3 will not appear. Phi 0, where is phi 0? It's here. So what will I get? L1. L1 has elements 2 and 3. It's acting here. So I guess with L1, I will get the element 2. So it's going to be A2 times V. Am I right? L1 is here. Well, there is minus Ig. Minus Ig, so let me keep the factors of I. And so there will be, the first will give me 0. So why did I write like this? The second will give me minus I. A1 V. Maybe it's correct what I wrote, the first element, okay. But you agree? And then the third, so this will be 0. And then L2, how does L2 look like? That's 3,1 is minus I. It's cyclic, so it gives me I, A2, V. suppressing the gauge index. And when I take this square, so I and I cancel, there are minus sign, but they are relevant, right? After all, what I'm taking is d mu phi 0 kind of transpose d mu phi 0. This will give me g square, v square, a1 square plus a2 square. There'll be a half. This will be my finite result. As expected. The mass must be proportional to vacuum potential value. The coefficient must be g, because that's the way you couple to the Higgs. Remember, I'm not going to do this anymore. Wherever there is a v, there is h also. So we always get this expansion 1 plus h over v when we take care of. We know how to calculate Higgs coupling to the gauge boson. Okay, we've done it in the U1 case. It's always going to be the same. We'll do it in the standard model when it's necessary here. This is a toy example, so I won't bother. But remember, if I needed to know how it's coupled to the Higgs, remember with v squared there is always 1 plus h over v squared, right? Because they go together. Which at the moment I'm not stuck, but this will happen. So it's kind of obvious what's going to happen. Every time the generator does not annihilate the vacuum, this guy will pick up the mass because it goes together with the generator. This is even easier to see than the Goldstone theorem. Okay, the Higgs. Call it the Higgs theorem. It is interesting that the non-abelian examples are often attributed to other people like Kibble and so on. The first people to publish paper on the Higgs mechanism were Engler and Broud and Higgs. Higgs maybe a little before with them, or maybe at the same time. And I'll comment on that. And then there were papers by Kibble and Kibble, Guralnik and Hagen and so on. And they all noticed that the gauge fields get a mass. They noticed that. And they noticed this important thing that the Goldstone boson disappears. People are worried about the Goldstone boson. They didn't know what to do with them. They also needed to understand how the gauge bosons would get a mass, and this was a beautiful solution of two profound puzzles, right? You eliminated the Goldstone boson, you ate it, and at the same time you gave gauge boson a mass. There was two things in the Higgs paper. Apparently, okay, the story is beautiful because he sent the paper noticing this. And this was acknowledged later on. The referee of his paper was Nambu, and Nambu told him you should find some other consequence of this work. Okay? Normally referees are not that generous. They often will just let you publish, and they publish the polar consequence. So in order to publish it, he realized that there was a Higgs particle associated with that. Not just the fact that the gauge boson get a mass and that the G disappears. He then noticed that there will be the Higgs particle, so the Higgs boson should be truly called Higgs boson. He was the first and the only person in that group at that moment. Engler and Brown didn't have it. But it's kind of interesting. He also did a non-abelian example, which is never attributed to him. People don't know. I'll send you the paper. I promised the thing. Okay, you should remind me, but I'll try to remember now. I'll send you the some of these original papers which are worth reading. It's interesting that he took, I'll comment on that later. Actually, we'll do it for homework. I'll give you a homework problem on his, he took an SU3 example with an octet. I don't know why. Why didn't he choose SO3 or something? Well, it's interesting when you write original work. You don't sometimes do the obvious, simple thing, right? You are there in the dark. Is this clear? Symmetry breaking tells me there are three originally generators minus one which remains. It's two broken generators. So I expect 2A with MA non-zero. And since the symmetry relates them, I expected them to be equal, and I got them equal. The SO3 example, all we need to remember is this. So you see the parallel. It has to be that parallel. Every time there was a Goldstone boson, now we have a massive gauge field. Someone has to eat that guy. Okay, we have to keep the number of degrees of freedom intact. A Goldstone boson must disappear because every time the gauge field gets a mass, you increase the number of degrees of freedom. One more, there will be one less. So, and we knew that, and we knew that when we did SO3 in the Goldstone case, right, we found that only 2 massless guys. So we knew that this would happen, okay.
Since physics is independent on how did we choose
the vacuum?
Our vacuum. We'll get our vacuum due to a combination of the generators, right? Not just like in this case.
Well, if you don't believe me, choose it in another direction. You will see that you will get the same result. Okay. I'll give you now one example in which I will show that explicitly, but I will sometimes do it and show you the physics does not depend on me. Sometimes I will use a physical argument. This is trivial. If you have to do a vector calculation, take it in the z direction. That's the definition of the axis. I have done nothing. I have just defined the z-axis here. That I can do. But if you don't believe it, take it in one direction or take it in 2 directions, then it will get messy, okay? Then I don't want to do it here, okay? But well, in the next example, let's do it in the next example. Let's do explicitly how it does not depend on the choice of the vacuum, okay? Since I've done it here. Okay, let's do it. So in other words, if this is clear, I will move now to the SU2 with the fundamental representation. Remember, fundamental is a doublet. We are after this at the end. Remember we said the Higgs boson, in order to couple to the fermion, there has to be at least a doublet in the standard model. Because left-handed fermions are doublets, right-handed are singlets. Someone has to talk to these guys. Or someone has to make them talk. If you wish, the Higgs boson is a messenger of the mass, of the force, if you wish so. As if there is some force that gives particle the mass. Okay, we'll be talking about that. So I want to do this next example. What happened when we did SU2 in the Goldstone case? What did we learn? How many Goldstone bosons do you remember? It was broken completely. So what do I expect? I expect 3 massive gauge field. The symmetry completely broken, so do I expect the masses to be same, similar, or different? I would expect them to be different completely, because the symmetry is completely broken. So it's a strange thing. To have masses the same normally means to have a symmetry behind it, okay? So let's do that. Well, I didn't even write the potential. It's the potential that we wrote before. So let's now not choose the vacuum. Okay, let's do something, because you may have doubts. So I know that the vacuum manifold is simply set of all phi 0, so that phi 0 dagger phi 0 is v squared, right? The minimum of the potential, which is 0 manifest, the way I write the potential. I hide the constant term. I choose it to be 0. Okay. So let's compute the gauge boson masses without even fixing. Let me not rotate now. In this example. So d mu is d mu minus Ig Ta a mu a. Sorry, why don't I write immediately? You don't have to. Which is sigma a over 2 a mu a. I don't know why I choose a now, but I could have chosen I. A is the same I. So now this is Pauli matrix. So what will d mu phi 0 dagger look like? This is a constant. I want to minimize the potential and kinetic energy. So what do I get? let's write like this. I'll get 1/2. There is g over 2 every time, you agree? So I'll get g over 2 squared. Then I will get phi 0 dagger, sigma A, A mu A, sigma B, A mu B, phi 0. Dagger, these are Hermitian, sigma A mu A, dat means that sigma B A mu B, that means that I took g over 2 squared here. What is this? This is 1/2 g squared over 4, phi 0 dagger. Sigma A sigma B is delta AB plus I epsilon ABC sigma C, phi 0, A mu A, A mu B. Correct? Well, this does not contribute because this is symmetric. They obviously commute, these anti-commute. Therefore, I find out two things interesting. One, I got the mass which I promised, A mu A, A mu A. I go to the three massive guys and I get phi 0 dagger phi 0, but that's v squared. So you see, I can do that. I could have chosen the vacuum, but I can do that. So if you don't believe me, do it for the SO3 case. Do it like this. So I go to 1/2 g squared v squared AA AA. I don't want to write the gauge index, the Lorentz index. Let's erase SO3. SO3 would have been very interesting if Schwiger were right. If we could have the standard model based on SO3, that would be beautiful. Charge would be quantized and so on. We just got wrong predictions. Then this would be the symmetry breaking. You would break it down to U1 because you need a photon. But the standard model has this extra U1 and so on, so this is not a picture. SO3 was just an illustrative example to understand how the symmetry breaking depends on the choice of the scalars. But this is what we are after, the doublet case. There is at least a doublet. But notice what I got strange. I got three massive A's. This is great, as expected. Maybe I don't put that. I also got an incredible thing, completely unexpected, that the masses are the same. Okay, it's 1/2 GV because of normalization. So in some books, people will speak to you, or you will hear people say that V is a fundamental parameter. Okay, they give you the number for that. That, of course, depends on a convention. It's not V that matters, it is MA that matters. I can normalize fields differently, so this coefficient may change, okay? V, of course, everything has to be proportional to V, but V is the way you normalize. You can normalize in your potential any which way you want, okay, with your fields. So the V does not have to be the same in the numbers that people give you in the books. In the standard models, you will often read 248 or 172 or whatnot. Well, someone is writing with a half, someone is writing without a half, okay? So don't worry about that. This is strange. This is mind-boggling. No symmetry whatsoever, and I get the part masses to be the same. That's a mirror.
Doesn't this imply that you can rotate in A space
because they have the same mass like the previous case.
No, in the previous case there was a symmetry that remained.
Yes, but like the form of the mass term is similar that we can rotate.
I don't know what you mean, but that symmetry is broken, so what right do I have to rotate once I break the symmetry? I didn't have three masses the same before. No, that argument cannot be good, because then why didn't I get three masses the same before? No, I go to one completely different from the others, because I broke the symmetry badly. I broke SO3 down to SO2, and I found out one massless, two massive. That was logical. The two had the same mass because the symmetry remained. In other words, what I mean here is that SU2, once again, we wrote this before, is broken down to no symmetry whatsoever through this phi 0. So there is no symmetry to correlate these guys. Apparent. Actually, there is. I've been commenting on this before. Actually, you knew what was the vacuum manifold of this? Why was it S3? Why was it S3? Because I can write phi as phi up, phi down. So phi 1 plus I phi 2, phi 3. I can write in many different ways. With phases, with whatever, but I can write like this also. And then, what is phi dagger phi? What symmetry is this? There is more symmetry, actually. It's not true that the symmetry is SU2. The symmetry of the gauge theory is SU2 because it depends on the covariant derivative that you write. That you decide. You know, you take a role of a god, of a creator of the universe. You can do that. When you write down a theory, you are playing God's role. You are saying, well, this I believe that the world is like this, and therefore I write this covariant derivative that determines how much of a local symmetry you have. But the symmetry of the potential is not in your hands. And better be careful. In the future when you do research, you can be easily wrong. There are so many wrong papers that one finds very often. Because people say, oh, I have this symmetry. It's not what you think that you have, it's what you get. The potential is quartic. It is quartic because higher term would damage the renormalizability. But in this case, it's simpler. This is the only invariant I can write, phi dagger phi. There are no other invariants. So I got extra symmetry. So what is going on? Well, remember, I have, in other words, I can write this potential. I can now introduce a phi. I could write it like this, you agree? As far as potential goes, I can write it like this. Well, it's I don't know if it's fair to use the same notation, but otherwise I'm introducing a new field. And phi transpose phi is this. Is sigma phi I squared. In other words, phi transforms, as you said correctly, into O4. Let me emphasize this phi. There is an SO4 symmetry here. How I can change the vacuum manifold? How I can choose it? Well, I can choose it like this, which is actually the same as I do here. Normally I would choose phi 0 to be 0V, and I would choose V to be real. You see, by an SU2 rotation, I can always rotate this into a lower component. That's the choice of the axis. If there's a phase here, I can eliminate it with a T3. There is still, when I move it in this direction, when I choose the phase, there is still apparently a rotation around T3. I use it to fix this. I can rotate more and eliminate phase. I can always choose this to be real. Okay, by the redefinition of the phase. So you see, this is the same vacuum as this one. In other words, I'm choosing phi 4 in the vacuum to be 0. So what does it mean that SO4 is broken down to SO3? In this case, in the gauge case, SU2 is broken down to 1. What does that mean? That I have 3 broken generators and I got 3 massive gauge fields. Here, how many generators SO4? 6. Antisymmetric. 3 times 4 over 2, or 4 times 3 over 2. So there is 6 minus 3 is 3. There are 3 broken, so I'm okay. It matches. Nothing bad happened, you know. If I got a different number, I would have to think. Maybe I would get a Goldstone boson, accidentally. Something that cannot be eaten by a gauge field, okay? But in this case, I'm okay. 6 to start with, 6 to remain. So in other words, there is an SO3 symmetry even after symmetry breaking in the potential. But the gauge fields are getting the mass from the phi field, whose properties you determine from the potential, the symmetry breaking. So in other words, it's this SO3 symmetry where we have to show that under this SO remaining symmetry that the gauge fields are a vector, are a triplet representation. This is called a custodial symmetry. It's called the custodial symmetry because it protects the masses of the gauge bosons. The reason they are the same is because of this SO3. This SO3 custodial protective symmetry. This is a very important lesson. There may be examples when you get a lot of symmetry in the potential and you may get an extra Goldstone boson. Then there's a question whether they pick up the mass when you go to the higher orders. Remember, I'm studying the quartic potential only. That's a 3-level potential. When you do the loops, who knows what can happen, okay? We'll talk about it when you learn more of field theory in the end. So this is an example in which the potential has more symmetry, but the symmetry breaking is exactly the same as the breaking of the gauge symmetry. There is an SO4 global symmetry, and it's broken down to SO3 global. So that means that there are 3 Goldstone bosons when I think globally, but there are 3 massive gauge fields, they're going to eat them. And how do I know that they're going to eat them? Well, remember, I will simply write that phi is e to the I, gi sigma I over 2, 0, v plus h. And then I do my rotation. This is how I wrote it in the Goldstone case. Now I would say that phi goes into e to the minus I, gi sigma I over 2, phi, 0 v plus h. I can I can get rid of these so-called would have been Goldstone bosons, we call them. They would have been Goldstones had I not gauged the symmetry, okay? But now they don't exist. And there are 3 of them because there are 3 broken generators that we solve by extraction. I'm going to pause and say a few words more here. I want to see it from a different angle. Let's try to show that the gauge bosons really behave as a triplet under the protective symmetry. So, and it's not obvious because the way I wrote it, it's hard to see what is going on. There it's a doublet, here it's some quartet. No, it's not obvious. So let's do something. Well, let's try to do it here. Imagine that I have my doublet phi. Suppose that I want to introduce the matrix, which is phi dagger. This is just a definition. Not phi dagger phi. This is a matrix now. This is not a number. What is this matrix, by the way? Let's see what it is. How did I call it? Phi up, phi down. Let's remain like this. Phi up, phi down. And this is phi up star, phi down star. This is what? This is, oh, I don't know whether I want this, but maybe I do. Phi up star. This may not be what I'm after. Phi d star, phi d, phi u star, phi d star. This may not be the smartest way to do it, but anyway, it's worth commenting here that if you want to study invariance, notice how sigma transforms, just to see, because people sometimes do this. Sigma transforms as u, sigma u dagger, you agree? So what would be the invariant here? Would be the trace of sigma. It is invariant, and if I look at it, what it is?
B squared.
No, these are fields. I'm not in the vacuum yet. No, this is precisely what I call phi dagger phi. Right? Phi u star phi u plus phi d star phi d. So this is one way that I can write my invariant. It's not just giving me what I want. Let me erase this. I think that maybe let me do the following. No, it will take some thought on the, a little more thought on the group theory. Let me do the following. Let me go to the standard model and then talk about the custodial symmetry, where we will see a similar phenomena, how it works. And I will tell you why. Let me leave this as a promise. Okay, this is not a convenient way of doing it. I'll have to talk about some SU2 properties that will be manifestly needed when we do the standard model. Let me pause this. Let me say that here there is a protective symmetry, and we have to show, that's our task, that this SOC symmetry precisely acts on my gauge fields. I suspect that it's there because I got it after the symmetry breaking, okay? But let me postpone the proof that to the standard model case when I have to introduce the tilde field. Let me not get thrust into the group theory algebra yet. Let's understand the physics. If this is clear, I won't say anything more on the SU2. Previously there would have been 3 Goldstone bosons, now we would eat them because 3 massive gauge fields, okay. We believe that we understand what is going on, we'll be more rigorous about it when I come back to it. You see, because with this we have machinery to go and immediately attack, and why don't we profit and do that? The standard model which is almost what we've done here, because what is the standard model? SU2 cross U1, this is the standard model symmetry. We often call this L and we call this hypercharge. That has to be broken if I want to create a realistic world. It would be nice actually to predict that, but I know it has to happen down to U1. This is the symmetry of the world in which you and I live. Apparently photon is massless. So what is going on? This is the first suspicion that I maybe should take a doublet. Actually all of the SU2 is broken. There is some rearrangement, this may not be the same U1, but who cares? The point is that the 3 generators will be broken, the SU2 symmetry will be broken completely. And that maybe tells me I should take a doublet. That could be the first game, okay? Because what we are doing now, we are asking the following question. What? 1967, there was a 61 paper of Glashow who constructed a gauge theory, but he had no idea what and how the masses would emerge and what they would be. He could make no prediction. Remember, Glashow couldn't tell you that there was going to be a photon. What he could do, he said, if you tell me there's a photon, I'll show you how I get the Z boson. But he didn't know how to break the symmetry, okay? So now that we know, we've learned, okay, we want to now go back in time, you know, freeze the time, and you and I construct the standard model, you will see that actually it's fairly simple, that we have a unique choice. So when I want to do the minimal standard model. Minimal, what it means, that I'll take the minimal set of particles whenever I can. So what Higgs representation to take? That's a question that was faced. Well, let's think even more deeply, not just as a group theory exercise. You and I know that the gauge bosons might get a mass, W and Z. But we know another thing, that the fermions might get a mass. We already commented on that. And we said the standard model, in order to define it, we had to tell you how, someone had to tell us how the fermions transform under this SU2 symmetry. The left-handed guys are the doublets, and only the left-handed guy. Minimal standard model, nobody ever saw right-handed neutrinos, I don't include it. We'll have a name for this. I will often call it QL, a quark doublet. And this is a leptonic doublet. This is a typical notation used by most of the literature. So the problem that I have in the standard model, I don't know how to give gauge boson the mass. See how useful the Higgs mechanism will be. And I don't know how to give fermions the mass because I cannot write the fermion master. For charge fermion must have this form. But it's impossible to write it. Forbidden by symmetry. In other words, I have to write QL bar dr, let's say. I can't write QL bar dr. Let me worry about the downpour. I must take the thing together because the symmetry tells me, okay? I can't take the piece from a doublet, okay? There is no this thing up and down. At this point, before I break the symmetry, there is only a doublet. Okay. Then we said, well, if it's impossible to write the mass term, maybe we can write the interaction. And we know that the field that has to be here is scalar. This is already Lorentz invariant. This has dimension 3, so I must put one field, dimension 1, and it must be a scalar. So whatever I put here must be a scalar. I need a scalar field for symmetry breaking anyway to give gauge boson a mass. It should be a scalar because I don't want to break a Lorentz symmetry. Therefore, I tell myself, well, I'll put that field. What are its quantum numbers? I can see immediately. It has to be a doublet. This is even more clear than just using the group theory reasoning about the gauge bosons, because I could use some other fields to get 3 massive gauge bosons. It's not only a doublet that does the symmetry breaking. We could cook it up. I'll find for you a larger representation to do something similar. But here the choice is unique. If I want to construct minimal standard model, this must be a doublet. Minimal means I just want to use one Higgs. Therefore, I use the same guy to give the mass to the gauge fields and mass to the fermion. I will call this Yukawa down, because this is where the down core couples. Okay, that fixes. Mehmet, that.
I'm kind of confused.
Okay.
Is this an invariant that you write here?
You tell me, do you think it's an invariant? Well, under what?
Under SU2.
Under SU2. Let's see. How does QL transform under SU2?
Like a doublet.
Okay, every doublet. So, doublet transforms like this. Every doublet in SU2 transforms the same way. I don't care whether they are fermions, whether they are bosons, whether they are gauge fields, they all transform the same way. So this transforms under SU2, okay. QL bar. U dagger, you agree? Q bar is Q dagger. Gamma 0 is a Lorentz. And this is a doublet, so it transforms with U. And DR is a singlet. And lo and behold, this is invariant.
So when you say scalar, you mean Lorentz scalar?
Oh, of course.
Not SU2.
No. I'll call SU2, I'll call singlets in order. I'll try to be careful. I don't promise this. Okay? Sometimes I may say scalar, but that would be careless on my part because I may confuse you. It's true that sometimes you speak in this term. But I'll say singlet. So, okay. There may be billions of particles in this world. Now you and I know that they must be singlets, except for those that we have seen. LHC is not finding them. They would have to lie at these energies. Therefore, the fields that, well, no, I take it back. I'm sorry. The message must be, forget what I said. Just forget what I said.
The second U is from 5.
I don't know. See, I should teach at 2. It's not at 11 when I'm waking up. Sorry, Mahmoud.
The second U is from the phi, how phi transform, or
Yeah, phi is a doublet.
but
Every doublet transforms in the same manner. It's a scalar and the Lorentz group. So where is the Lorentz group? It's here in this indices, alpha, alpha, which I don't write.
okay. But we put the condition on when U dagger which transform the quarks and U which transform phi to be the same U, because we could have U1, U2 and
No, there is only one SU2. What do you mean? There is just one SU2. I wrote SU2. I didn't write SU2 cross SU2. There is just one rotation. I could have more SU2 groups. You know, I could cook up a very complicated model that wouldn't be minimal. I have an SU2 group for leptons, SU2 group for quarks, whatever, SU2 group for Higgs. Everything would be possible. I'm writing the minimal model with one and the same SU2, and I want to minimize the number of fields that corresponds to the reality I want to describe. So for example, I would take here, if there is one generation, I would take one generation. If people see 2 generations, I would take 2 generations. And that's why I took a great courage on Kobayashi Maskawapa to say there are 3 generations before there were 3, okay? At some moments you have to give up minimality when the things are not working, but what you and I try is to sort of, it's a last resort. We try to do that really when nothing else works. Without minimality we cannot make predictions. It may be amusing, we will get a lot of fun. We can play with non-minimal, we can speculate as much as we want, but it becomes too easy. It's like playing chess and changing rules. Okay, so I hope that this guy will get a vacuum expectation value so I can get the mass, obviously. We found it in the U1 case. From here I got the mass. What about the up quark? What am I going to do for the up quark? I want to now write Yukawa up, QL bar, UR, 5. Can I write this? Let me pause. Will this be invariant?
Under SU2, yes.
Uh-huh. Okay. But I need the whole symmetry to be respected. What about U1? You cannot be invariant under U1. Remember my formula for charge in the standard model? Or maybe I emphasize here, right? So these guys obviously carry hypercharge, and they obviously carry different hypercharge. And you know that it's a profound difference. For example, this one carries 4/3, because T3 is 0 for them, this one carries -2/3. So what can I do? Well, I want to have a minimal model. Well, you can tell me, take another Higgs doublet with a different hypercharge. Okay, we didn't specify the hypercharge here. Can you compute? Let me see how quick you are. Can we compute what the hypercharge? I already fixed the hypercharges of quarks. I could have started with the Higgs, but I decided to have this formula for charge. Remember I said I can have some coefficients here, and since this is arbitrary, I'm going to normalize my charge like this. I could have taken also minus T3, or I could have taken a linear combination of these. This is a convention. The T3 is diagonal, and so on and so forth. Hypercharge of dr is -2/3. That's trivial because it's just twice the charge. But what about the hypercharge of QL? I gave you a trick to remember for all season. I told you a trick in a doublet immediately. You can look at larger representation. T3 adds up to 0. So sum of the charges is sum of the hypercharges. But the hypercharge must be the same. In a doublet, hypercharge of a doublet is the charge of the up component plus the charge of the down component. Why does the hypercharge why does it have to be the same? Because SU2 commutes with U1. These are independent symmetry. The generators commute. So of course the particle in a doublet here, they must have the same hypercharge, otherwise this wouldn't be a commuting symmetry. You would mix them. You see, it also tells you that electromagnetic charge cannot be hypercharged. You could have said, why didn't they write here charge immediately, separately? They can't be because charges are different in a doublet. So how much is this? 2/3 minus 1/3, 1/3. So 5 has hypercharge doublet. So 5 is a doublet with hypercharge plus 1. Okay? So, and this guy, what should this guy carry? This is not 5 here. This is 4/3. So you can immediately that here there must be a guy with a hypercharge -1. So what should I do? It's just some simple group theory. That's why I want you to know group theory really in your fingers so that you can address such.
It can be a doublet.
Sorry?
It can be a doublet, I don't know.
Yes, it must be a doublet. No, but we said that here it must be a doublet. This is a doublet, this must be a doublet. But it cannot be 5. 5 has hypercharge +1.
It can have a linear combination
Or what?
of two terms that
Which linear combination of what? Which two terms? I must live with doublets. I cannot break them into pieces. 5 star? Okay, I'll try 5 star. Let me try to, okay, 5 transforms as U5. 5 star transforms into U star 5 star. This is not a doublet. SU2 is not a real sort of, doublet is not real. It's pseudo-real, we say. Yes?
we can make it doublet by
Okay, but what did you do in the Lorentz group? You didn't take lambdas. You didn't take 5 star. Psi C. How do you define in the Lorentz group, a digression? Psi transforms as lambda psi. You took psi C. What was psi C? It's almost what it is, if you remember. It was simply I sigma 2. So if this is to work, what should I put here? This is called phi tilde. And phi tilde transforms as U phi tilde. Because of documentation properties of sigma 2. We actually saw it the other day. So you have always field, and this is not surprising. If I have an electron, I have a positron. Whenever I have a field, I have an anti-field. Automatically, it's just a complex conjugate. The only thing you have to write it a little more carefully, but with the spinors we are used to do that. You don't work with psi dagger, you want with psi bar in order to transform correctly the invariant, okay? By the way, in SU2, whenever you have two doublets, phi 1 dagger, phi 2 is invariant. You agree? Because the doublets transform the same way. That means that phi tilde dagger, phi is also an invariant. This is also doublet. What is this? This is phi transpose I sigma 2 minus I sigma 2 phi. This is the famous other. What this is just simply anti-symmetrizing spin. This is an anti-symmetric combination of two spins. This is how you used to do in quantum mechanics. So you were already used to this phi tilde, only your notation was different, okay?
Is this a second invariant, or is this the same invariant that we at first had? Because for this group we must have just one invariant.
No, when phi is complex, these are different invariants. For example, this is 0. For scalar fields, this is 0. For scalar fields, I can only write phi dagger phi. For spinors, I have a choice. And I think it was Nicolas who remembered, but there will be two mass terms. There is also my Rana mass term and the Dirac mass terms. We have to talk a lot about it. Okay, you've been introduced to that, but this is never too much. Okay, that's the crux of, if you wish, of modern particle physics and of field theory. This is the holy grail of today's neutrino physics, which is the physics of beyond the standard model. That's where the standard model failed, we will see, okay? It's learning how to distinguish, how to live with these two possible invariants. In this case, this will be different invariant. This one would be real. Notice it's different. In the sense, Soto-Majorana is real, whereas Dirac is complex, okay? Whatever I mean by that will be more clear, but you can see the analogy here. Fortunately, this vanishes, so our potential ended up being very simple. Otherwise, we would have to work with a complicated potential. We had only one invariant. And that's why there is a custodial symmetry and so on and so forth. And since I want to introduce this phi tilde field, I want you to be familiar before I speak of custodial symmetry. It plays a fundamental role here. I have to do the same thing for the electron. You see, now I'm going to be okay. This is good. You see, the contour numbers of the standard model allow you to have a very minimal structure, okay? This is unique. When you go to the theories beyond the standard model, you will see that you will need more than one Higgs multiplier. The beauty, the simplicity, the elegance, whatever you might say about the standard model, many people say, oh, this is not a nice theory for this or that reason, aesthetics. The beauty lies in minimality. That's very important because that gives you predictivity. You should appreciate that. If I try to do for the electron, I would write LL, bar, ER, and I put either phi or phi star. It's very easy to see that it's phi. Because here hypercharge is -2, here hypercharge is -1, and so on. Please check. You have the formula. The hypercharge is determined from this formula. The charges you ask to remember. After all, there are very few fundamental particles, fortunately. The number may look large because the generations repeat, but basically up and down quark and electron, that's all you have to remember. Neutrino lives in the same doublet with the electrons, so it has the same hypercharge. So my attempt to construct a minimal standard model by having a single Higgs field worked with a single phi, I get all Yukawa interactions. And I suspect, we have to check that I will get all masses. We'll check that in a second. I showed you how the choice of the vacuum did not impact the gauge boson masses, okay? But I'll be choosing one vacuum for simplicity. Now when I want to read all these particles, it's much easier, okay? I will do that always. Just the choice of coordinate system. See if you can ask me something here. Because now we should start reading of the consequences. So let's do that in some order. You see, just to remind you anyway, psi is UL, UR. These guys are spinors under rotation. That's why psi C behaves like that. Just to remind you, you've seen that UL transforms as e to the I sigma over 2 psi. I don't know how I put no phi. UL in UR. A quick reminder, I sigma over 2 delta minus I phi UR. You see, when you wrote psi C, there was this phi tilde hidden. This is rotation, the theta piece. And this was boost. Actually, very few of you did this. When I asked, what is this boost, to write that tangent phi we took one direction is velocity. Tangent hyperbolic, okay, when I say the boost. A lot of you said, well, this is the boost, as if it's obvious. Okay, the boost is velocity. That's what I call a boost. Right? This is what one gets. It's sort of a little exercise. So notice under rotations, these are, the thing to remember about them, left and right spinners are spinners. So you will use in your dreams. And after boosts, you will remember, well, they are sort of left and right. They will go in the opposite directions. Okay. So the thing, of course, about boosts is that these are now imaginary. Therefore, I don't have permission generators. I cannot have a finite dimension unitary representation of Lorentz group. That doesn't exist. I found a finite dimensional representation, but my generators are a bit strange. These are normal Hermitian. These are anti-Hermitian. Anyway, what is hidden there inside is the fact that spinners I have two ways of writing spinner, okay, which is inside C. Please, this is something to keep in mind. Okay. These were side comments. So let's read of the cosine questions. Let's see if I manage. So I'm going to rotate phi 0. But remember, this is to say that phi is just this. There are no other fields. I'm in the unitary gauge. I want to read off the physics. There is nothing else. The G's are eaten. I eliminated them before. Okay. The covariant derivative, let's see, read of the gauge fields. D mu is d mu minus IG. Well, let's write like this. TA A mu A minus IG prime minus IG prime hypercharge over 2 is a convention times B. There is nothing profound here how I write this. This is just a definition of G prime. Normalization. B I normalize the same way as I normalize these guys, okay, in the kinetic energy. This is just my definition of G prime. Remember there was an important parameter which was weak mixing energy. The ratio of the two coupling costs. Or better to say tangent. This is the covariant derivative, right? From the covariant derivative, what I will get is a kinetic energy for H. That's trivial. PA is a Pauli matrices. So this had a form. Let's write this here. I G over 2, and then it has a form. This matrix, how does it look like? A3? No, 1 over 2, I'm sorry. 1 over 2, GA3 plus G prime B, A1 minus IA2. Think about it while I'm hiding. I think this is correct. Or not. G. There is G here, right? Maybe you meant this. Maybe there is something else wrong, I don't know. But
A3 has same coefficient. Minus.
or maybe it's better to put like this to be correct. At the end, it will not matter because we will. But I'm sorry, of course. There'll be a squared, so the sign will. I'm sorry. Sure. So I will get 0 d mu h. Well, I'll include it in a second. What do I have? Off diagonal. This will only give me off diagonal. So I'll get minus I g over 2 a1 minus I a2 v plus h. I can carry it, all of it. And here there will be d mu h minus I over 2, and then minus GA3 plus G prime B this is my doublet times V plus H. I think this is correct. You agree? The off-diagonal piece is the only this one. This one will give 0. I think this is correct. But please check me.
Mu h and thousand times.
So it was better the way I wrote before. Wanted to write. This will be a correct. Thank you. This is correct. I don't know why I kept this, but this is all of it, so I kept it, the kinetic piece. The derivative of H. Nicolas? No. So it's easy to see from here. D mu phi, let me write symbolically, 1/2 will be 1/2 d mu h squared, which we expected, plus 1/2 g squared over 4, a1 squared plus a2 squared, plus 1/2 g squared, no, there is no g squared, 1 over 4, can write like this. This is the I could have written it immediately. It was obvious that this was going to split the covariant term. This you and I already checked a number of times. This is the famous mass for the W bosons. I will introduce linear combinations of A1 and A2, which I call W bosons. And here is the physics of this photon and Z boson. Okay. It's okay, right? I can erase this. This was rather elementary, but anyway, it's good to occasionally do even the boring things. So I define W plus minus as 1 over square root of 2 of A1 minus I plus A2 A1 minus plus A2. And if you want a mu index, you would add a mu index. There was this minus sign, we saw it when we wrote the interaction. Here it's not clear what the sign would be, okay? So this is called the mass of the W. And here I'm finding an interesting thing, that there is just one massive gauge field, not two. Okay, this is a typical mistake that I've seen in the homeworks. The people don't organize this much term, because if I had written separately, I would have A3 square and I would have B square, and I could think that both of them get a mass. No, if I organize it correctly, I see that only one linear combination gets the mass. I could have guessed that. When I wrote this, I can see that all the TA phi 0 are non-zero, and the hypercharge acting on phi 0 is non-zero. It seems that 4 generators are broken, but not true. It's easy to see here that Q electromagnetic on phi 0 is 0. This is my choice of Q, how I wrote it with this particular convention. I could have taken a minus sign on some linear combination, then this would be the other way around, okay? But the way I chose it, this is a neutral guy, okay? And this guy is unbroken, okay? And that tells me, of course, that only one gauge neutral fields will be massive, okay? You see what we are saying here? We are predicting the photon. Unlike Leshow, who couldn't say anything because he didn't know what and how the symmetry would be broken. What Weibull can do by writing this particular minima Higgs doublet model, you now have, if you believe in the standard model, then the photon is massless, period. The magical question, why photon is massless, you would answer, because the theory of the world is the standard model. The question disappeared. He cannot have a small mass. Okay, it makes a very firm prediction, the minimal standard model. Photon is strictly massless. And notice that I can write this, in other words, mw squared is 1/4 g squared v squared. From here. There is an interaction with Higgs, but that we've seen before. It's not surprising. It's proportional to the mass. We'll write about that. And the second, this term I can write as 1/4 g squared plus g prime squared. And then I can write minus g a3 plus g prime b over square root of g squared plus g prime squared, everything squared. Why did I do it? I wanted to normalize my fields. My A3 and B were nicely normalized with my kinetic energies. I didn't write down, but I normalized them the same way. So the physical field must be normalized the same way. This is a massive gauge field. In other words, I'm predicting that this particular combination, orthogonal to this, is from here, and there is V squared. Let me keep. No, sorry, this was just this piece. So what I'm predicting that MA is 0. And what is A? A is orthogonal to this. G prime A3 plus GB over square root of G squared plus G prime squared, which is sine theta W A3 plus cosine theta WB. This is the photon. How do I know? Because it's orthogonal to this combination that has a mass. There were 2 fields to start with, there are now still 2 fields. One is massive, one that has the master, and the guy orthogonal to it is massless. And I've learned what I suspected from the beginning, that photon is hidden inside. It's a little bit of SU2 and a little bit of U1. For example, if theta W goes to 0, the photon will go into the hypercharge guy, into B. Because then they will be separated, G prime and G, and I will have the sp2 symmetry, which would be broken. And there is a Z boson, which is orthogonal to this, which is, we often write GA3 up to the sign minus G prime B divided by G squared plus G prime squared. In other words, this is cosine theta W A3 minus sine theta W B. You can stick Lorentz indices if you like. This is a profound prediction of the standard model. Minimality gave us something deep.
How does normalization actually work? Like when we are talking about the mass of W, it's evident to see, but
the mass of W is, I can say nothing because I don't know what V is. You agree? W is, I have to determine from experiment. And we'll talk about it, how you determine it already from the low energy experiment. Before even finding W, what I can predict here is the Z boson mass. Mz squared. Notice, it's bigger than MW. And maybe I can write without squares. Why do I need the squares? Cosine theta W, right? Cosine theta W is the ratio of G over square root of G squared plus G prime squared. Well, I cannot determine the scale. How can I determine the mass of the W if I don't know what physics is describing? I've just broken the symmetry. So I need now to know what W does. I look at some low energy process, but I've made a profound prediction now. Much more exciting than the one that Gleshow had. I'm also predicting the Z boson mass. There is a serious check because I will be measuring theta W. Remember, theta W entered into the neutral currents. Actually, you were measuring it. When you looked at the Z boson decay, you were measuring theta W. You found out that theta W 0.23 or 0.25. I took 0.25 and I got a reasonably good agreement with the, I was checking at my numbers. I've sent you my numbers anyway. I don't know whether I'm a mistake. They were a little too good, my numbers, with 0.25. But I made two mistakes. I took 0.25, which is wrong. It should be 0.23. I also pretended a big quark is massless, for example. Big quark is not massless. So maybe that made me. So we predict the photon. And by the way, the photon, we knew the form of the photon. If you look back in what we did with Gleshow, photon had this form. We had to have this form in order to couple correctly. This is a generic thing, okay? I can show you either in the class or we have a homework problem to show you that this can be extended to products of many gauge groups. The photon is always a combination like this. We predict the photon and we predict the mass of the Z boson. The interactions of the Z boson that already Gleshow predicted. Nicola.
What we did previously was we actually enforced to be a chargeless boson.
Yes.
So then we get was one of the combinations was
right. We said there is one guy which couples to the charge, and it turned out to be that guy. Okay. Now we now know that there is we found that Q cannot be broken. Doesn't matter what you do. No matter what gymnastics you do, one linear combination will remain unbroken. And the neat exercise is to see that, for example, not just with a particular choice of vacuum. I may give it as a homework, I'm not sure. You can play with it, you say, oh, but if I put V1 and V2 here, then it's very, yes, it's hard to see then, but it can be seen. You see, because then you are, if you are not, this particular convention I'm choosing goes together with T3 being diagonal. But that's a convention. Who says that T3 is diagonal? I can take a linear combination of T1, T2, and T3 to be diagonal. No, I can change public matrices. I will stick to this convention, which corresponds to this formula for charge, which corresponds to these values of hypercharges that I've chosen. I have precisely normalized like this, so that I have you see my upper component has more charge because T3 is plus a half. If I had taken a minus sign here, then I would have reversed the thing. Okay, it's a convention. This is the simplest, the most logical. I don't know.
You said that we can predict here the masses of the boson, but we still have the interaction with the Higgs field also here.
Yeah, of course. No, we'll talk a lot about it. It's hidden. That also will be predicted. But before it comes to that, the mass of the Z-ball is predicted. For example, for theta W roughly 30 degrees, you find out that MW is 80 GeV. We'll come to that, and this becomes predicted to 90 GeV. This was a great success of the lab experiment.
But previously we talked about this custodial symmetry.
Oh, we'll come back to it. Yes, but okay, let's.
That was
No,
how is expressed here? That was my question.
Well, the custodial symmetry is here. Notice that if there is something going on here also. If I take theta W0, then I will get mz equal to mw. All the masses will be the same. I have to recover the SE2 result by separating U1, okay, just by going to that limit, and there is no mixing between the two gauge groups, okay. So I'll have to talk about custodial symmetry. Well, notice that the potential is the same potential. Well, I didn't write it, it was the same potential. I couldn't write another term in the potential. I wanna discuss that.
So the mass
Not today, obviously, because I wanted to profit from what we learned about SU2, and I wanted to reduce the tilde field, which was here crucial, not just as a algebraic group theory thing. Okay, we'll have to postpone the rest of the consequences. Okay, we need one more lecture on Wednesday to see the consequences for other fields in the theory. We have to see how all the fermions get a mass, and so on. And then, of course, we'll get into the physics of the Higgs a lot and some of the features.
So
Yes.
the mass that you speak about to measure the experiment is the mass of this mass term, which doesn't have anything to do with the Higgs, plus the mass term which comes from Higgs boson.
No, this came from the Higgs boson. This came from here. This is a vacuum space. It came from the Higgs. Without the Higgs field, they would have been massless. Of course, it's not.
I cannot see this because
Oh, they were massless. This came from a covariant derivative. No, you saw it. SE2 cross U1 gauge symmetry implies massless field. I can have this trick of what we call Stuckelberg introducing the extra degree of freedom of fixed gauge, but those fields are not there. You wouldn't do me anything. These guys are massless. There was no. I didn't write the explicit breaking. This is very crucial. I cannot explicitly break the symmetry. This is a theorem. I've indicated the problems and I will come back to them. That if you give explicitly them, which is called the Proca thing, masses to gauge bosons, the propagators are bad and the theory is non-normalizable. I have to do. This is very crucial. There cannot be small amount of explicit breaking. That would destroy everything. This is the picture. If you find that these relations are not, violated, okay, we are in trouble. And the Sandu model passed this test with a fantastic, great precision now, in 1/1000 basically, okay. The two loops calculation has been done, and the through loops in many things have been done or being done, okay. This is now converging to a high precision theory the way QED was. The Higgs physics will be more delicate, okay? When I speak of the high precision theory, I mean the gauge boson physics, the weak interaction physics. That's high precision. Higgs, of course, not. As you know, I had LAC, not a high precision machine. You need, okay, we'll talk a lot about machines. We need sort of leptonic machines to have clean physics.
Isn't H is the Higgs field?
H is a Higgs field.
But you
So here it's a couple.
yeah, but we have also V, which is
V is just
a constant.
yes, V is the thing that fills the V measures the amount of the non-triviality of our vacuum. You know, it's some kind of ether. You know, it's like, as I said, it's like living in the water.
Yes.
If I can heat up my system, then I will go from water to vapor, let's say, okay, V will disappear.
We express our masses in terms of V here.
Yes, of course. This is what it is. The masses of particles are coming out of nothing. There is a magic. There is a magic. The things when you see a magician, you know, taking the pigeon out and he book a handkerchief or whatnot. We've done magic. Spontaneous symmetry raking is a magical thing. Nothing, I mean, out of vacuum. A vacuum was supposed to be nothing. You never cared about the vacuum. You must say, forget it, okay, I just determine the ground state to know that I have a ground state, and then I look at my excitations, okay. Ground state here, you know, is the floor. I don't care about that thing so much, okay, the thing is here, you know, I look at the difference between the table and the floor, and then worry if this falls down, or even more if my iPhone falls down. But, you know, when I have my feet on the ground, I'm okay. But what we are learning is the vacuum itself has a rich dynamics. And it will be important to test it. We have to come back to these issues. How you and I will really know that the world is like this? And it's not that somehow it's mimicking this world. How we will know that you may say, well, I don't know, I really have to believe that it came from V, some renormalizability you're talking about. Maybe actually it's you know, mass is given explicitly. And it looks like this only, right? We'll have to think about deep physical consequences of the Higgs mechanism. Which means that we have to study a lot of Higgs boson itself. You will see there will be a number of probes that are crucial. We should still worry. We are still not there. There could still be in principle some deviations, okay? The Higgs is being probed as we speak. It's a very slow, painstaking process. Maybe we stop the public part. That's it, right? I can turn it off.